Hey guys, and welcome to another installment of Marvelous Mechanics. Today we'll be discussing the principle of adhesion. For that, we'll be taking a look at that rectangular mass that is sitting at this white surface inclined by the angle theta. The purple arrow marks the gravitational force of the mass. This force can be divided into two components, namely the blue one, pushing the mass against the surface, and the red one. Some simple angle tracing proofs that the angle theta shows up again right there. For a better visual understanding of what the red component does, let's put a copy of it at the left edge of the mass. Let us call this force A. Using basic trigonometry, we can easily determine the value of the force A. Furthermore, we see that this force moves the mass downward along the incline, as long as there are no other forces keeping it from doing that. Let's keep that in mind. Let's also look at what happens if we increase the angle at which the surface is inclined, so we get a better understanding about the dependencies of A. We can clearly see that when theta gets bigger, so does the component of the gravitational force that tries to move the rectangle. However, the system is static, which means that there must be forces that the surface exerts on the rectangle that keep it from moving in any direction. Let's make these forces visible in the sketch. We call the forces that keeps the rectangle in place A0 and N. Naturally, if the value of the force that tries moving the body, namely A, is less or equal to the value of the force which tries to keep it from moving, namely A0, the phenomenon of adhesion occurs. The value of A0 is the product of the adhesion coefficient, a measure for a surface's roughness, and N. If you feel overwhelmed, don't worry, I've got you, because now we're going to use this principle on some examples. For the first example, we'll consider this tilted rod. We need to compute the minimal angle between the ground and this rod, at which adhesion still occurs. We know the rod's weight force, the roughness of the ground, and the fact that the wall isn't rough at all. We also know where to draw on the rod's weight force, namely at its center of mass. In order to understand the assignment better, let's visualize what would happen if the ground wasn't rough enough to prevent the rod from slipping. We can clearly see that the rod is slipping to the left along the ground. Thus, we can deduce that the adhesion force which the ground exerts on the rod and that tries to prevent the rod from slipping must be pointing to the right. Knowing that, we can now substitute the ground and the wall with the forces each of them exert on the rod. Now that we have a complete free body diagram of the rod, we now need to write down the three equilibrium conditions for the static system according to the coordinate system on the top left. If you're still having trouble understanding and formulating moment conditions, feel free to check out my latest video on the principle of moments, where I explain the concept in a clear step-by-step manner. Let's get back to the task at hand. Maybe you remember this formula for the value of the adhesion force. It'll sure come in handy soon. But first, let's rearrange the x and y conditions. Next up, we try to rearrange the moment equation in a way that, in the end, we have a fully defined expression for the contact force C as a function of the given weight force of the rod. Having C fully defined is useful to us because the x equation on top states that A is equal to C, which means we can simply substitute this expression, providing us with yet another definition of the value of the adhesion force. The y equation states that N is equal to G, which is a given force. So let's substitute this into the formula for A, so that this formula is now fully defined as well. We are now left with two perfectly correct expressions for A, both of which consist solely of known values. The first is merely the definition of the adhesion force, and the second is derived from the free body diagram. Let's write both right-hand side terms as one equation that we try to solve for theta. Filling in the value for the adhesion coefficient, we can see that the two g terms cancel out perfectly. Doing one more rearrangement leaves us with the conclusion that sine of the angle we are looking for is exactly the same as the cosine of this very angle. As it happens, sine and cosine are equal at the angle pi over 4 radians, which is the final solution for our problem. For the next example, I want you to look at the system of two masses that are connected with each other by a rope. We need to calculate the maximum value of M2 such that M2 is just light enough to not move M1. From the information we are provided with, we can predict the motion of the bright rectangle. However, in reality, this motion is prevented by the roughness of the white surface, which we need to keep in mind. Let's take a closer look on the forces that are exerted on the bright rectangle. The row force tries pulling the rectangle along the incline, whereas the weight force tries pulling it downwards. For convenience, we consider this tilted coordinate system and divide the weight force into its components according to this coordinate system. Knowing where the angle theta shows up again, we can now easily denote definitions for G's components. Notice G's y component pushes the rectangle against the surface, whereas the x component points exactly at the opposite direction of the rope force. But remember, the surface itself exerts forces on the rectangle as well, namely the contact force N and the adhesion force A. The value of the adhesion force that opposes the movement induced by F is calculated using this formula with which we are now quite familiar. This free body diagram now allows us to express the equilibrium conditions according to our tilted coordinate system. Since we're interested in an expression for the relation between M1 and M2, and the rope force is itself a function of M2, it's sensible to rearrange the x equation like this. After we've done this, let's substitute in the definitions of the two variables a and gx. Sadly, we are still oblivious of the value of the contact force, but simply rearranging the y equation like this solves our problem. Better yet, now that we know its value, we can substitute it into the expression for the rope force. Not only can we do that, but we can also simply substitute in the definition for gy into the top expression, so that the rope force definition now solely consists of known values. Lastly, we substitute the variable f for its definition and are left with a perfect equation that we just need to solve for a relation between M2 and M1. Since we want to make the relation between the two masses as simple as possible, factoring out M1 times G seems to be a good first step. Secondly, we know the value of theta, so we just might as well sub it in. The values of the sine and cosine function at the angle pi over 6 are just common knowledge and help us simplifying this equation. After subbing in the known value for our adhesion coefficient, the only thing that's left to do is performing really simple and elemental rearrangements. So this is a maximum value for M2 as a function of M1. If you put this in a calculator, you'll notice that M2 isn't allowed to be much bigger than M1 at all. Let's do a little recap on what we've learned today. At first, we learned that the adhesion force prevents bodies from sliding over each other, provided that the adhesion force isn't smaller than the force trying to induce the sliding. Secondly, we learned that the value of the adhesion force cannot be derived from only looking at equilibrium conditions, but is much rather calculated using a formula consisting of the adhesion coefficient and the normal force. Lastly, we learned that sometimes the standard Cartesian coordinate system is not the most convenient way to make free body diagrams or equilibrium conditions, especially when dealing with masses on inclined planes. Thank you for watching this video. Feel free to leave a like and subscribe to my channel. Please leave feedback and questions in the comments. See you next time at Marvelous Mechanics.